Hi, welcome to Problem Solving Expert. In this video, I'll be talking about GR&R studies using ANOVA method. By the way, before watching this video, I highly recommend that you watch Problem Solving Expert, repetibility studies to validate the measurement system, and especially PSE 2020, which is GR&R studies, range method, and means and ranges method. By the way, ANOVA method is a much more accurate method to calculate the variability of the measurement system. I have said in previous videos that usually we are having a transformation process. In this transformation process, we are having inputs and we are having outputs. And by the way, in order to know how good was the process or how good is the product, usually we take a sample and we make a measurement. And then what we get is the data. With the data that we are obtaining, we are having a mean, we are having a standard deviation, and we can calculate ppm, sigma level, etc., which is our baseline performance. But the variability of the data is not the variability of the transformation process only, but it is the variance of the transformation process, can be the variance of the product or the variance of the process, plus the variance of the measurement system. And both variances combined, we are getting the variance of the data. Also, I have said that the mean of the data is not the actual mean of the product or process, but it is the mean of the product or process plus the error because of the measurement system. The error of the measurement system, usually it is obtained through calibration studies, which is not part of what I'm talking about in this video. But I'm doing more precision studies, which are studies to evaluate how big is the variability of the measurement system. The calculation of the standard deviation of variance of the measurement system, it is much more accurate using ANOVA method than using the ranges method or the means and ranges method. The reason of that is because in the previous methods, the other methods that I have used in PSE 2020, I have said that the standard deviation of the measurement system is equal to the mean of the ranges divided by D2 star. And D2 star is coming from a table. Then this is an approximation to calculate the standard deviation of the measurement system. But this is not very accurate. In ANOVA method, we are calculating the standard deviation of the measurement system, especially for repetibility, as the sum of squares divided by the degrees of freedom square root. And this method is much more accurate in order to get the standard deviation of the measurement system. By the way, I'll be using the same example that I have used in the video that I have used the means and ranges method, which is the long method. I have 10 parts, and those parts are measured twice for each of the inspectors, and I am having 2 inspectors. These numbers are exactly the same numbers that I have used in that example for the means and ranges method. Well, let's start to calculate the repetibility, the reproducibility, and by the way, also I'll be calculating the interaction part to part and the inspector, and also the variation part to part because of the parts. So there are more components that I can get from the ANOVA method. Well, let's start. In the video Problem Solving Expert 210, we have talked about the GR&R Type 1 or uncertainty studies. In that one, basically we are just evaluating the percentage of repetibility, because the study is done only by one person, one measurement instrument or equipment, one place, one method, and one part measured several times. So we are just evaluating the variation because of common sources of variation related to the measurement system, and that is the repetibility. In video Problem Solving 220, I have talked about the GR&R ranges method, which is the short method, and also the GR&R means and ranges method. For the ranges method or short method, basically we are evaluating the total variability of the measurement system, which is the total GR&R. But we don't know how much of that total variability is because of repetibility and how much is because of reproducibility. Also, in video problem solving 220, I have talked about the long method using the means and ranges method. In that one, we are evaluating the percentage of repetibility, the percentage of reproducibility, and the percentage of GR&R, which some people state, some people call it like the equipment variation, which would be the repetibility, the appraiser variation or operator's variation, which is the reproducibility, and the total variability, which is the GR&R. Well, in this video, we are talking about the ANOVA method. For the ANOVA method or analysis of variances method, we are using exactly the same long method in terms of the design. Usually 10 parts, measured at least twice by each of the inspectors, and usually we are having several inspectors or several appraisers. So I strongly recommend that you take a look to video problem solving expert 320 to analyze the ANOVA method, and also which is a hypothesis test, which is the analysis of variances, and also take a look to PSE 220, which is the GR&R study. So today we are going to combine both the analysis of variances, which is a method to compare means using variances, and also, well, the design of the study, which is the long method for the GR&R. For this method, the ANOVA method, we are getting the percentage of repetibility, the percentage of reproducibility, the total GR&R, but in addition, we are also obtaining the interaction part operator. By the way, there will be another video which will be focused on the interpretation of the GR&R, because there are many things to talk about the interpretation. So in addition, we are going to get this interaction. Just one quick comment. The ANOVA method that I have talked about, which is the PSE 320, is just for one factor. But today, for the GR&R, we are doing an ANOVA method, but for two factors, because one of the factors will be the inspectors, that is one factor, and the other factor will be the part. For the ANOVA method, we want to evaluate the total variability in the system, in the study. The whole variability and the whole variability of all the data. But that whole variability is the result of the variability between inspectors, the variability part to part, we are having several parts, 10 parts, the variability because the interaction, which is the interaction inspector part, and also the natural variation or the variability because of the error, which is because of all the rest of the common sources of variation. Well, let's start. The first thing to do is to calculate the sum of squares. By the way, I remind you that I have said that the standard deviation is equal to the sum of squares divided by the degrees of freedom square root. So, if we want to evaluate the standard deviation because of the repetibility, for instance, I have to get the sum of squares of the repetibility, which in this case will be the sum of squares of the error, the natural variation, divided by the degrees of freedom of that error or that natural variation. But let's start first analyzing or calculating all the sum of squares for each of the components. The sum of squares total, which is the total variability, the sum of squares of the inspectors, the sum of squares part to part, which is between parts, and the sum of squares of the interaction inspector part to part, and the sum of squares of the error. Well, let's start calculating the sum of squares total, which is the total variability of the system, the total variability of the whole data. To get the total variability for the whole data, we are having this formula, which is the sum, let me put that one this way, the sum of squares total. The sum of squares total, which is the total variability, is the sum of the data from inspector 1 to inspector 2, because we are having two inspectors. We are having the inspector A and we are having the inspector B. So we are having 2 as A, the number of inspectors. But not just that, also we want to have the sum from J equal to 1 to J equal to 10. Why is J? What is J? J is the number of parts, and we are having 10 parts. As you can see here in the study, we are having a total of 10 parts. So we are having from J equal to 1 to 10 parts. And in addition, the sum from K equal to 1 to 2. 2 are the trials or replicates that we are having. For this case, we are having 2 trials for each inspector, 2 trials for each inspector. We can have 3 or more trials as well, but for this specific example, we are having just 2 trials. Of the data, the Y, which is the measurement for this case, of I, J, K square. And subtract from that the measurements of all the inspectors, all the parts, all the trials, the square divided by total number of measurements. So we are having a total number of measurements equal to 40. The reason of that is because we are having 10 parts times 2 trials, that's 20, times 2 inspectors, which is 40 total measurements. Well, let's do one thing at a time. The first thing that I want to calculate is y dot dot dot. Y dot 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 will be equal to the value of all the inspectors, all the parts, all the trials, and that is the sum of everything. So in this case, we have to sum everything, which is 12.5 plus 12.7 plus 16.0 and so on, 15.4 and so on. I have to do all the sum of all the data of both inspectors, both trials, and the last one will be 15.6 plus 15.5. Well, let me do the calculation. The sum of all the measurements is 564.2, but that should be squared and divided by the total number of measurements. In this case, y dot 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 squared divided by n would be 564.2, all of that square divided by 40 measurements. And well, let me do the calculation. The sum of all the measurements for all the inspectors, all the parts, all the trials, squared divided by 40 is 7,958.041. This value will be used for each of the calculations for the sum of square totals, the sum of squares of the inspector, the part to part as well, and the interaction also. Then I will put that value here, which is all the sum of the measurements of all inspectors, all the parts, all the trials, square divided by total number of measurements is equal to 7,958.041. Okay, next step is to calculate the first term of the sum of square totals, which is this one. I will calculate that one now. So, the sum from inspector 1 to inspector 2, from part 1 to part 10, from trial 1 to trial 2 of the measurement inspector I, part J, trial K, square. And that will be equal to first inspector, first part, first trial. First inspector, first part, first trial, 12.5. And that is square. Plus first inspector, first part, second trial. First inspector, first part, second trial, 12.7 square. Plus first inspector, second part, first trial. First inspector, second part, first trial, 16. And so on. So I have to square each of the measurement of all the parts, all the trials, all the inspectors. So at the end, I will be having 15.5, which is the last one, square. Okay. Let me do the calculations. The result was 8001.96. With that, now we can calculate the sum of squares total. And the sum of square total will be the first term, which is 8001.96, minus the second term, which was 7958.041. Okay, let's do the calculation. Well, we are having the first term, which is 43.919 for the sum of square totals, which is the first term. I'm going to put that value here. So I will put the sum of squares total is equal to 43.919. Now, of that variation, I want to know how much of that variation is because the variation between the inspectors, the sum of squares because of the inspectors. Well, we already have this term, which is the 7,958. Now, let me calculate this term. I will place here. And I will do, for the first term, the sum from inspector 1 to inspector 2 of the measurements of the inspector I, all the parts, all the trials, square, divided by the number of parts times the number of trials. Well, the first thing is that I have to get the sum of all the parts, all the trials for inspector 1. And that will be the sum of all of these measurements. And also I'm going to get the sum of all the parts, all the trials for inspector 2. And that will be the sum for all these trials. Well, let me do the calculations. The sum of all the measurements for inspector A is 281.1. The sum of all the measurements for inspector B is 283.1. Well, let's then do that. So that will be the measurements of inspector 1, all the parts, all the trials. That is 281.1. And that is the square. Divided by B, which is number of parts, times N, which is number of trials. We are having 10 parts times 2 trials for inspect A, plus, because that is the sum, the measurements of inspector 2, all the parts, all the trials. The measurements of inspector 2, all the parts, all the trials, is 83.1 square divided by also 10 parts, 2 trials. Okay, let's do the calculations. Well, we already have this first term for the sum of squares of the inspector, and with that we can calculate the sum of squares of the inspectors. And the sum of square of inspectors is equal to the first term, which is the sum, 7,958.141, minus measurements for all the inspectors, all the parts, all the trials squared divided by total number of measurements, which is this value, 7,958.041. And well, basically that difference is equal to 0.1. And that value, well, will be the sum of squares of the inspectors, which I will put it here, which is sum of squares of inspector is equal to 0.1. Well, now I want to calculate the variation part to part, the variation because of all the parts, which is all of these. For that one, I have to get the measurements for all the inspectors, part J, all the trials. Well, that means that I have to get all the inspectors, part 1, all the trials, and I have to put the sum here. So that will be the term, Y, which are the measurements, all the inspectors, part J, all the trials. So I have to do the sum of those 4 and put the value here. The sum of those 4 and put the value here. Well, let me do the calculations. Now we are ready to calculate the first term for the sum of squares part to part. And that will be the sum from the part number 1 to the part number 10 of the measurements for all the inspectors, part J, all the trials square, divided by number of inspectors times number of trials. In this, for this case, we will have all the measurements for all inspectors, part 1, all the trials. All the measurements for part 1, all the inspectors, and that will be 50.9. Square divided by 2 inspectors times 2 trials. 2 inspectors, 2 trials. Plus, because that is a sum, all the measurements for all inspectors, part 2, all the trials. And that will be 62.8 square divided by 2 inspectors, 2 trials. Plus, all the inspectors, part 3, two inspectors, 2 trials, and so on until the last one, which will be all the measurements for all inspectors, part 10, square divided by 2 inspectors, 2 trials. Okay, let's do the calculations. With that, now we can calculate the sum of squares part to part. And that will be the sum of squares part to part is equal to the first term, which is the one that we have just calculated, 8,000.655, minus all the inspectors, all the parts, all the trials squared divided by 40, which is this term, 7,958.041. Okay, let's do the calculation. The sum of squares part to part, because that is the variability among each of the parts or created because of the parts, that is 42.614. Now, let's calculate the sum of squares of the interaction inspector part to part. For this calculation, we need 4 terms. We already have the sum of squares part to part, which is this one. We already have the sum of squares of the inspector, which is 0.1. And also we already have the sum of squares total. For the sum of squares total, we are having this one, 43.919. Then the only missing term that we have to calculate is this one, which is the measurements of part 1, inspector 1, all the trials, divided by number of trials, plus inspector 1, part 2, all the trials, and so on. That means that now I have to do the sum of these two values and put them here. The sum of these two values and put them here. So basically that term is going to be the measurements y of inspector 1 part J, all the trials. And here will be the measurement of inspector 2 part J, all the trials. So I have to do the sum of all the trials for all the parts for inspector 1 and for inspector 2. Well, let's do the calculations. Now we are ready to calculate the first term for the sum of squares of the interaction. And that will be the sum from the inspector 1 to inspector 2 and the sum from the part 1 to the part 10 of the measurement for inspector I, part J, all the trials, square divided by number of trials. So that will be the measurement for first inspector, first part, all the trials. For first inspector, first part, all the trials will be 25.2. And that is the square divided by number of trials, 2 trials, plus inspector 1, part 2, all the trials. Inspector 1, part 2, all the trials. 31.4 square divided by 2. Plus inspector 1, part 3, all the trials. Inspector 1, part 3, all the trials. And so on. So I will continue doing the sum of each of the parts, all the trials, for all the inspectors. So the last one will be 31.1 square divided by 2. Well, let's do the calculations. Now we can calculate the sum of squares of the interaction inspector times part to part. And that will be sum of squares of inspector times part to part. And that is the first term, which is 8001.13. 8001.13 minus, well, this term, which is 7,958.041 minus the sum of squares of the inspector. And the sum of squares of the inspector is 0.1 minus 0.1 minus the sum of squares part to part minus the sum of squares part to part, which is 42.614. And that is equal to, let's do the calculation. With that, we are having the sum of squares of the interaction inspector part to part, which is 0.375. Now we have to calculate the sum of squares of the error. The sum of squares of the error is the sum because of all the other factors that we are not taking in consideration. The natural variation of all the other conditions like the environmental changing conditions and so on. That also variability because of the equipment, all the conditions that we are not taking in consideration. That's why the sum of squares of the error, which also will be called for the GR&R sum of squares of repetibility, will be the total variability minus the variability because of the inspector, minus the variability part to part, minus the variability because of the interaction. Well, let's do that one. And then the sum of squares of the error, as I have said, that will be the repetibility, is equal to sum of squares total. The sum of squares total was 43.919 minus the sum of squares of the inspector, and the sum of squares of the inspector is 0.1 minus the sum of squares part to part, which is 42.614 minus sum of squares of the interaction, and that will be 0.375. Okay, let's do the calculation. Well, that is the variability because of the all other factors that I'm not taking in consideration in the analysis, which will be the sum of squares of the error or the sum of squares of the repetibility. The next step is to do what is known as ANOVA table. And in the ANOVA table, I will have the sum of squares, I will have the degrees of freedom, and I will be getting the means of squares. And the mean of squares will be the sum of squares divided by the degrees of freedom. With that, also we are going to get F calculated to determine if the factor that we are analyzing is significative. Well, let's do the ANOVA table. Okay, well, let's do the ANOVA table. For the ANOVA table, here we are having the sources of variation, which is the total variation, the result or the sum of the sum of squares of the inspector plus the part-to-part variation plus the interaction inspector times part-to-part and the error or repetibility, which is the sum of squares that we just have calculated previously. Now let's calculate the degrees of freedom. The degrees of freedom for the inspector will be A, which is the number of inspectors, minus 1. In our case, number of inspectors is 2. Minus 1, we are having equal to 1 degree of freedom. Now, the degrees of freedom for the part-to-part will be number of parts, B, minus 1. In our case, the number of parts is 10 minus 1. We are having 9 degrees of freedom. For the degrees of freedom of the interaction would be A minus 1 times B minus 1. For this case will be 2 minus 1 equal to 1. times b minus 1, which is 10 minus 1, equal to 9. 1 times 9, also we are having 9 degrees of freedom. The total degrees of freedom will be n, a, b, and n, which is equal to capital N, which is the number of inspector times number of parts times number of trials minus 1. In this case, we are having 2 times 10 times 2 is 40 minus 1, we are having 39 degrees of freedom. Then from 39, I have to subtract all the degrees of freedom. 9 plus 9 plus 1, that will be 19. 39 minus 19, so we are having here a total of 20 degrees of freedom. Now, let's calculate the means of squares. The mean of squares is equal to the sum of squares divided by the degrees of freedom. Then, for the means of squares for inspector will be 0.1 divided by 1, and that will be the sum of squares. For the second one will be 42.614 divided by 9. For the third one, it will be 0.375 divided by 9. And for the last one, it will be 0.83 divided by 20. Well, let's do the calculation. Here we are having the means of squares. Now let's calculate f. F basically is the mean of squares of the factor divided by the mean of squares of the error or of the natural variation. So for the first example will be 0.1 divided by the mean of squares of the error is 0.0415. For the second one, the f would be 4.7349 divided by 0.0415. And for the third one will be 0.04167 divided by 0.0415. Well, let's do the calculation. Here we are having f calculated. Now, what should be done is to compare the f calculated against f from table, from f Fisher table. Basically, the concept is this one, as I have said in video PSE 320. Here we are having the f Fisher distribution. The f Fisher distribution starts from 0, and then we will have the f from table. The f from table. So here we're having f of table. This is the region of reject null hypothesis. Reject null hypothesis. And this is this section related to fail to reject null hypothesis. The null hypothesis basically is that the variance because of the factor is equal, let me put it with this other color, the variance of the factor is equal to the variance of the error, of the natural variation. Then if we are getting this, the f calculated is greater than f from table, then that means that this variation that we are calculating is not natural variation, is not because of the error, but that is a significant factor. The variability is greater than the natural variation. But if we get the fail to reject, that means that there is not enough statistical evidence to conclude that the variation of the factor is significant. Because, well, it can be, that variation can be because of the natural variation. Then the next step is to get F from tables. Let's take a look to the tables, assuming and alpha equal to 0.05, assuming alpha equal to 5% of error, 0.05, which is 95% confidence level. Well, let's take a look to the tables. For F Fisher table and alpha equal to 5% or 95% confidence level, using 1 degree of freedom for numerator, which is the inspector, and 20 degrees of freedom for denominator, which are the degrees of freedom for the error or repetibility, we are having an F value of 4.35. As well, taking a look to the same table and using 9 degrees of freedom for numerator, which are the part-to-part degrees of freedom, and 20 degrees of freedom for denominator, which is the error or repetibility, we are having an F value from table of 2.39. Also, we will use 2.39 for the F value for the interaction inspector times part to part, because we are also having 9 degrees of freedom for the interaction and 20 degrees of freedom for the error or repetibility. Now let's analyze the F values. F from table for the inspector, it will be 4.35, and the F calculated is 2.41. Since the F calculated is smaller than F from table, we are in region fail to reject null hypothesis. That means that there is not enough statistical evidence to conclude that the variability because of the inspector is significant. Maybe that variability that we have calculated is because of the natural variation, because of all the other sources of variation. That means that the inspector, the variability because of the inspector, is not significant. Now, let's see for the second case, which is part-to-part variation. The F from table is 2.39. Since the F calculated is 114, which is far, far away from here, 114, we are in region reject null hypothesis, which means that the variability part to part is significant. That variability is not a natural variation, but that variability is significant. And finally, well, the 2.39, which is the value from table, and the F calculated for the interaction, inspector part to part, is 1, which is very small. 1, which is in region fail to reject null hypothesis. That means that is not significant. Then, actually, we should have only the repetibility variation for this GR&R study. And I should not calculate interaction, or even I shouldn't have reproducibility, because the variation of the inspector is not significant. Now, for training purposes, let me call it that way, I will assume that everything is significant. That's an assumption which is not real, but I will assume that to let you know, to teach you how to calculate the percentage of repetibility, the percentage of reproducibility, the percentage of the interaction, and the total GR&R. To give you all the components, I will assume that everything is significant, but I shouldn't, as I have said, because not all the sources of variation are significant. Well, I will start doing that, the calculation for each of the terms, assuming that all of them are significant. Assuming that everything is significant, now I'm going to calculate the variance. And the variance for the inspector will be the mean of squares of the inspector minus the mean of squares of the interaction divided by the number of parts times the number of trials. So for this case, it will be mean of squares of the inspector, which is 0.1, minus mean of squares of the interaction, which is 0.04167, divided by B, which is 10 parts, and 2 trials, which is 10 times 2, 20. For the variance part to part, it will be the mean of squares part to part, which is 4.7349, minus the mean of squares of the interaction, which is 0.04167. And the variance for the interaction will be mean of squares of the interaction, which is 0.04167, minus mean of squares of the error, which is 0.0415, divided by number of trials, which will be 2 trials. And the variance for the repetibility or for the error is basically the mean of squares of the error, which is 0.0415. Well, let's do the calculation. Well, we already have the variances for all the sources of variation. Now, let's get the total variance, and the total variance will be the variance of the inspector, which is this one, 0.002917, plus the variance of the interaction, and the variance of the interaction will be this one, 0.00008333, plus the variance of the error. The variance of the error is 0.0415. Well, actually, that is not the total variance, but that will be the variance because of the measurement system. The total variance should include the variance part to part, but that variation part to part is not part of the measurement system variation. That's why we are excluding from the total variance the variance part to part, and that will be the variance for the measurement system. So actually this is the variance for the measurement system. With that, we are ready to do the calculations, which are repetibility, reproducibility, and gauge R&R, and as well the interaction. Well, let's proceed to do those calculations. Then, the variance for the measurement system, 0.0445, which is the sum of the variances related to the measurement system. The variance because of the repetibility, that will be the variance because of the error, because of all the sources of variation that we are not calculating separated, which is 0.0415. The variance because of the inspector, 0.002917, which is the first one, the first variance because of the inspector. And finally, we are having the variance because the interaction, which is this value, 0.0000833, which is this one. Now, the variance because of reproducibility, that will be the sum of both variances, the sum of the variance of the inspector plus the sum of the interaction, and we will call to that one reproducibility. With that, now we can calculate the total variability because of the measurement system. Assuming that we are having a normal distribution and assuming 99% confidence, 99% of the area, this total range would be equal to 5.15 standard deviations. Then that's what we are going to get here, 5.15 standard deviations. Now, Sometimes, especially in automotive industry, instead of using 99%, they use 99.73%. Then, instead of using 5.15 standard deviations, they use 6 standard deviations. That is for automotive industry. So, under those situations, instead of calculating 5.15, use 6 standard deviations. But I will use 5.15 standard deviations. Then, for the first case, we are having that the GR&R will be equal to, let me show you that, the GR&R is equal to 5.15 square root of the variance of the GR&R, which is 0.0445, and so on. For instance, to get the repetibility, I will use 5.15 square root of the variance, which is 0.0415. And so on. I will do 5.15, the square root of this, 5.15, the square root of this, and 5.15, the square root of this. Well, let me do the calculations. Well, here we are having the total variability of the measurement system, 1.086. Of that, how much is because of common causes of variation, how much is because of reproducibility, and of that, how much is because of the inspector, and how much is because of the interaction. Now, is that good or bad? Is that acceptable or not acceptable? Well, we have to compare that variability against the tolerance in order to get the percentage of the tolerance. And also, we have to compare against the total variability of the process. Then we are going to have the percentage of process variation. Well, as I have said in video problem solving 220, the GR&R percentage against tolerance is equal to GR&R divided by the tolerance times 100. For this case, the tolerance will be, I'm using the same example that I did use in PSE 220, and I have said that the upper specification limit is 16 and the lower specification limit is 12. Then we are having that the tolerance is upper specification limit minus lower specification limit. Then, for this case, the tolerance is equal to 16 minus 12. That's why, which is 4. That's why the percentage of GR&R against tolerance will be the GR&R, which is 1.086 divided by the tolerance, which is 4, times 100. By the other hand, I have said that we can have the percentage against process, and the percentage of GR&R against process is equal to the standard deviation because of the measurement system divided by the standard deviation long term, which is the standard deviation that we have calculated while we were doing our baseline performance, which includes both the variability of the actual transformation process, the actual variability of the transformation process, plus the variability of the measurement system times 100. For this example, well, we are having that the standard deviation of the measurement system will be the square root of the variance. Then, the percentage of GR&R against process, it can be the square root of the variance of the measurement system, 0.0445, which is the standard deviation, divided by the standard deviation long term, which is 2.3 times 100. Well, let me do the calculations for not just for the GR&R, but also for repetibility, for reproducibility, and of that for the inspector and the interaction. Let's do the calculations. Well, here we are having the percentage against tolerance and percentage against process, using the ratio of standard deviations. Although there will be another video with more details about the interpretation of the GR&Rs, in general terms, let me tell you that if the percentage of GR&R is against tolerance is smaller than 10%, then the measurement system is good. If this one is greater than 30%, then it is bad. And if it is between 10 and 30%, we should take a look to the percentage against process. If the percentage against process is smaller than 20%, that means that at this point the measurement system is acceptable. And that means that right now we can use the measurement system because the measurement system is not introducing a lot of noise to the data that we are collecting from the process. But at the end of the project, we should do, if we are reducing the variability of the process, if we are having a project to reduce the variability of the process, at the end of the project that we have reduced the variability of the process, we have to check again the measurement system to confirm if it still is acceptable, if not greater than 20%. And if the percentage against process were higher than 20%, that means that we have to stop until we fix the measurement system, because that means that the measurement system is introducing too much noise to the data that we are analyzing, the data of the process that we are analyzing. So at this point, I would say that it is good, it is an acceptable measurement system because this is not greater than 30% and this is smaller than 20%. Well, basically that's it in terms of how to analyze a GR&R study long method using ANOVA method. Thank you very much. See you next time.